In the vast expanse of our universe, where countless stars illuminate the darkness of space, there exist objects of such extreme density and power that they challenge our understanding of physics itself. These are neutron stars, the remnants of once magnificent stellar giants, now compressed into spheres so dense that a single teaspoon of their material would weigh as much as a mountain on Earth. Imagine the night sky above you, filled with stars of varying brightness and color. Each star represents a magnificent fusion reactor, burning hydrogen into helium at temperatures of millions of degrees. These cosmic furnaces shine for billions of years, bringing light and warmth to their surrounding planetary systems. But stars do not live forever. Like all things in our universe, they follow a cycle of birth, life, and eventually death. For stars much larger than our Sun, perhaps 8 to 20 times more massive, their deaths are particularly spectacular and violent. When such a star exhausts its nuclear fuel, the delicate balance between the outward pressure of fusion and the inward pull of gravity is disturbed. Without the energy from fusion pushing outward, gravity suddenly becomes the dominant force, and the star begins to collapse upon itself. What follows is one of the most energetic events in the cosmos, a supernova explosion. The outer layers of the star are blasted outward at speeds approaching 1/10 the speed of light, briefly outshining entire galaxies. But it is what remains at the center of this cosmic cataclysm that concerns our story tonight. For in the heart of the dying star, where pressures and temperatures reach unimaginable extremes, matter is compressed beyond anything we can experience on Earth. Under such extreme conditions, electrons, which normally orbit around atomic nuclei, are forced into the protons at the center of atoms. This merger creates neutrons, subatomic particles that normally reside within the nucleus. As this process continues throughout the collapsing core, almost the entire star is converted into a sphere of tightly packed neutrons, hence the name neutron star. The transformation is truly mind-boggling. A star that once spanned millions of kilometers across is crushed into a sphere merely 20 kilometers in diameter, roughly the size of a small city. Yet this tiny object contains more mass than our entire Sun. It is as if someone took an object 1 million kilometers wide and pressed it down to the size of Manhattan Island, while preserving all its original matter. This extreme compression creates densities that are difficult for human minds to comprehend. The density at the center of a neutron star is estimated to be over 10 to the 14th grams per cubic centimeter. To put this in perspective, a single sugar cube-sized piece of neutron star material would weigh approximately 1 billion tons on Earth, equivalent to the weight of Mount Everest. Time behaves differently around these cosmic oddities as well. The immense gravity of neutron stars warps space-time itself, causing strange relativistic effects that Albert Einstein predicted in his theory of general relativity. A clock placed on the surface of a neutron star would tick noticeably slower than one here on Earth, a phenomenon known as gravitational time dilation. These stellar remnants also spin at incredible rates. As the original star collapses, it must conserve angular momentum, much like an ice skater who pulls in their arms to spin faster. This causes neutron stars to rotate hundreds of times per second. Imagine an object with more mass than our Sun, spinning faster than the blades of a kitchen blender. The forces involved are absolutely staggering. As we drift through the cosmic night together, consider these stellar ghosts, these dense stellar corpses that represent matter at its most extreme state. Neutron stars stand as cosmic laboratories where the laws of physics are stretched to their limits, where the familiar rules that govern our everyday existence begin to break down and transform into something else entirely. Throughout our journey tonight, we will explore these enigmatic objects in greater detail. We will venture into their internal structure, where matter may exist in forms never seen elsewhere in the universe. We will discover how some neutron stars become cosmic lighthouses, beaming radiation across the galaxy with clock-like precision. We will encounter magnetars, neutron stars with magnetic fields so powerful they could wipe a credit card clean from halfway across the solar system. We will witness the cataclysmic mergers of neutron stars, events so powerful they create ripples in the fabric of space-time itself and forge some of the heaviest elements in the universe, including gold and platinum. We will learn how astronomers observe these distant objects and what mysteries about them remain unsolved. So close your eyes and let your mind wander into the depths of space, where gravity crushes stars to their limit, where matter is compressed to its maximum density, where the cosmos reveals some of its most profound secrets. The story of neutron stars is a tale of extremes, of transformation, of cosmic violence, and cosmic beauty. It is a reminder that even in death, stars continue to shape our universe in remarkable ways. As you drift towards sleep, picture these dense stellar remnants spinning silently in the darkness of space, their powerful magnetic fields steering beams of radiation like cosmic lighthouses, sending signals across the vastness of our galaxy. They have existed for millions, sometimes billions of years, watching as galaxies collide and new stars form from the ashes of the old. They are among the most extreme objects in our universe, yet they follow the same physical laws that govern our own existence here on Earth, reminding us of our connection to the cosmos. Let the rhythmic pulse of these distant stellar remnants guide you into peaceful slumber as we begin our exploration of the densest objects in the universe, the enigmatic neutron stars. In the vast tapestry of space, stars live out their lives in cosmic balance, their immense gravitational pull inward perfectly countered by the outward pressure of nuclear fusion. This delicate equilibrium allows stars to shine for billions of years, spreading light and warmth across the universe. But every star faces an inevitable end when its nuclear fuel becomes exhausted and the balance shifts. For some stars, this shift leads to one of the most spectacular transformations in the cosmos, the birth of a neutron star. To understand how neutron stars come into being, we must first appreciate the life cycle of massive stars. Our story begins with enormous clouds of hydrogen gas drifting through space. These vast molecular clouds, spanning dozens of light years across, contain the raw material from which stars form. Under the influence of gravity, these clouds gradually contract, becoming denser and hotter as they collapse inward. When the density and temperature at the core of these collapsing clouds reach sufficiently high values, approximately 10 million degrees Kelvin, nuclear fusion ignites. Hydrogen atoms combine to form helium, releasing tremendous amounts of energy in the process. This energy produces an outward pressure that counteracts the inward pull of gravity, and a star is born. Stars that will eventually form neutron stars begin their lives with at least 8 times the mass of our Sun, though typically not more than 20 times as massive. These stellar giants burn through their hydrogen fuel much more rapidly than smaller stars like our Sun. While our Sun will shine steadily for about 10 billion years, these massive stars exhaust their core hydrogen in mere tens of millions of years, a cosmically brief existence. As the hydrogen at the core becomes depleted, these massive stars undergo a significant transformation. The core contracts and heats up, eventually reaching temperatures high enough to fuse helium into carbon and oxygen. Meanwhile, hydrogen fusion continues in a shell surrounding the core, causing the star's outer layers to expand dramatically. The star becomes what astronomers call a red supergiant, a bloated stellar giant with a radius that could extend beyond the orbit of Mars if placed where our Sun is. This pattern repeats several times in massive stars, with progressively heavier elements forming at the core. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally, silicon fuses into iron. Each new fusion reaction requires higher temperatures and occurs more rapidly than the last. While hydrogen fusion might have powered the star for millions of years, the final stages of silicon burning might last only a day or two. The star develops an onion-like structure, with layers of different elements arranged by atomic weight, the heaviest elements at the center, and the lightest at the surface. But when iron forms at the core, the star reaches a critical juncture. Iron represents a turning point in nuclear physics. Unlike lighter elements, fusing iron does not release energy. Instead, it requires an input of energy. The star has reached the end of its fusion journey. Without the energy from fusion pushing outward, the balance of forces suddenly shifts. Gravity, which has been held at bay throughout the star's life, now becomes the dominant force. What happens next occurs with breathtaking speed. The iron core, no longer supported by fusion energy, collapses under its own weight. This collapse happens at an astonishing rate, with the core shrinking from roughly 5,000 kilometers in diameter to just 20 kilometers in less than a second. During this catastrophic implosion, the core temperature soars to over 100 billion degrees Kelvin. Under such extreme conditions, atomic nuclei are crushed together so tightly that electrons, which normally orbit around atomic nuclei, are forced into the protons at the center of atoms. This process, known as electron capture, transforms protons into neutrons through the release of neutrinos, ghostly particles that barely interact with matter. In fact, during this collapse, an enormous burst of neutrinos is released, carrying away about 99% of the energy of the supernova. As this process continues throughout the collapsing core, almost the entire star is converted into a sphere of tightly packed neutrons. But the collapse doesn't continue indefinitely. When the density approaches that of an atomic nucleus, approximately 400 trillion grams per cubic centimeter, a new force comes into play: neutron degeneracy pressure. This pressure arises from a quantum mechanical principle called the Pauli exclusion principle, which states that no two identical fermions, such as neutrons, can occupy the same quantum state simultaneously. As neutrons are packed closer together, they resist further compression, creating an outward pressure that can halt the collapse, provided the core's mass doesn't exceed about 2 to 3 solar masses. Meanwhile, the sudden halt of the core's collapse sends a shockwave reverberating outward through the star's outer layers. This shockwave, energized by the tremendous neutrino flux from the core, blasts the star's outer layers into space in a spectacular explosion known as a Type II supernova. For a brief period, the exploding star can outshine an entire galaxy of hundreds of billions of stars. As the dust and gas from the explosion clear, what remains at the center is a newborn neutron star, a bizarre object that defies our everyday understanding of matter. This neutron star contains roughly 1.5 times the mass of our Sun, compressed into a sphere only about 20 kilometers in diameter. The gravitational force at its surface is 200 billion times stronger than Earth's gravity. A marshmallow dropped from 1 meter above a neutron star would hit the surface with the energy of 1,000 hydrogen bombs. The density of a neutron star is almost impossible to comprehend in human terms. 1 teaspoon of neutron star material would weigh approximately 1 billion tons on Earth, equivalent to the weight of Mount Everest. If you could somehow stand on a neutron star, you would be flattened to a thin layer, just 1 atom thick. The gravitational field is so intense that it bends light, making it possible to see more than half of the star's surface from one vantage point, as light from the far side curves around toward the observer. The birth of a neutron star also creates conditions for some remarkable properties. The conservation of angular momentum during the collapse causes the neutron star to spin extremely rapidly. Just as a figure skater spins faster when pulling their arms close to their body, the dramatic decrease in radius causes the rotation rate to increase tremendously. While the progenitor star might have rotated once every few weeks, a newly formed neutron star typically rotates several times per second, with some spinning hundreds of times per second. Similarly, the conservation of magnetic flux during the collapse amplifies the star's magnetic field to extraordinary strengths. The magnetic fields of neutron stars can be trillions of times stronger than Earth's magnetic field, and in special cases called magnetars, they can be even thousands of times stronger than that. The region surrounding a newly formed neutron star is a chaotic environment. The supernova explosion leaves behind an expanding shell of gas and dust, enriched with heavy elements forged both during the star's life and during the explosion itself. These elements, scattered through space, will eventually become incorporated into new stars, planets, and potentially life forms. Indeed, many of the elements essential for life on Earth, including oxygen, carbon, and nitrogen, were created in the hearts of stars and distributed through supernova explosions. Not all massive stars form neutron stars, however. If the core of the collapsing star is sufficiently massive, typically more than about 3 solar masses, even neutron degeneracy pressure cannot halt the collapse. In such cases, the core continues to implode, eventually forming a black hole, an object so dense that not even light can escape its gravitational pull. The exact boundary between neutron star formation and black hole formation remains an area of active research in astrophysics. In the aftermath of the supernova, the newly formed neutron star doesn't remain static. It undergoes a period of cooling and adjustment. Initially, the temperature of a neutron star is around 1 trillion degrees Kelvin, but it cools rapidly through neutrino emission. After about 100 years, the temperature drops to about 1 million degrees Kelvin, still incredibly hot by human standards, but significantly cooler than its initial state. As we contemplate these remarkable stellar remnants, born from catastrophic stellar deaths, we are reminded of the cyclical nature of the cosmos. The elements forged in the hearts of stars and scattered by supernova explosions become the building blocks for new generations of stars, planets, and life forms. In this grand cosmic cycle, neutron stars stand as extraordinary waypoints, marking the transition from one stellar generation to the next. The birth of a neutron star represents one of the most extreme transformations in the universe, a process where the familiar rules of matter and energy are pushed to their limits. These dense stellar remnants serve as cosmic laboratories, allowing scientists to study physics under conditions impossible to replicate on Earth. As we continue our journey through the night, we will explore the strange and exotic physics that governs these remarkable objects and their significance in the broader cosmic story. Deep within the heart of a neutron star lies a realm where physics, as we know it, is stretched to its absolute limits. Here, in these cosmic laboratories of extreme conditions, matter exists in states found nowhere else in the universe. The extraordinary densities, pressures, and magnetic fields create an environment where quantum mechanics, nuclear physics, and general relativity intersect in profound ways, challenging our understanding of the fundamental nature of reality. To truly appreciate the bizarre physics inside neutron stars, we must first understand what prevents these stellar remnants from collapsing further into black holes. The key lies in a quantum mechanical effect called neutron degeneracy pressure. Unlike the pressure we experience in everyday life, which results from the thermal motion of particles, degeneracy pressure arises from a fundamental principle of quantum mechanics known as the Pauli exclusion principle. This principle, formulated by Austrian physicist Wolfgang Pauli in 1925, states that no two identical fermions, such as neutrons, can occupy exactly the same quantum state simultaneously. As neutrons are packed closer together in the collapsing stellar core, they are forced into higher and higher energy states because the lower energy states are already occupied. This creates an outward pressure that can counteract the inward pull of gravity, effectively halting the collapse. Neutron degeneracy pressure represents a fascinating intersection of the quantum world and the cosmic scale. It is purely quantum mechanical in origin, arising from the wave-like nature of particles at the subatomic level, yet it manifests on a stellar scale, supporting the weight of an object more massive than our Sun. This pressure is what establishes the delicate balance that allows neutron stars to exist in stable form, rather than collapsing into black holes. The internal structure of a neutron star is thought to consist of several distinct layers, each with its own exotic physics. Starting from the outside and moving inward, we first encounter the atmosphere, an incredibly thin layer only about 1 centimeter thick. Despite its minimal thickness, this atmosphere is crucial for determining the spectral characteristics of the neutron star that astronomers observe. Beneath the atmosphere lies the outer crust, a solid lattice of heavy nuclei embedded in a sea of electrons, somewhat similar to metals on Earth, but under much greater pressure. These nuclei are primarily iron and elements with similar atomic weights, arranged in a crystalline structure. As we descend deeper, the pressure steadily increases, forcing nuclei closer together and causing electrons to merge with protons, forming neutrons. This process, known as neutronization, gradually changes the composition of the crust. At a density of about 400 trillion grams per cubic centimeter, approximately 1,000 meters below the surface, we reach the inner crust. Here, the nuclei become increasingly neutron-rich and are surrounded by a fluid of free neutrons that have dripped out of the nuclei. This neutron fluid is believed to be in a superfluid state, a quantum mechanical phase of matter with zero viscosity, allowing it to flow without any resistance. Descending further, at a depth of about 1 kilometer, the distinct nuclei disappear altogether, and we enter the outer core. This region, which comprises the bulk of the neutron star's volume, consists primarily of a dense fluid of free neutrons, with a small percentage of protons and electrons. The neutrons here are also thought to form a superfluid, while the protons likely form a superconductor, a state of matter that allows electric current to flow with zero resistance. The coexistence of superfluidity and superconductivity in the outer core creates a fascinating environment where quantum effects manifest on a macroscopic scale. Superfluids exhibit remarkable properties, such as the ability to flow up the walls of containers, defying gravity, and to pass through tiny pores that would block normal fluids. In the context of neutron stars, superfluidity affects how the star cools over time and how its rotation rate changes. Finally, at the very center of the neutron star lies the inner core, a region of such extreme density, exceeding 1 quadrillion grams per cubic centimeter, that even neutrons may be unable to exist in their normal state. The exact composition of the inner core remains one of the greatest mysteries in nuclear astrophysics, with several theoretical possibilities under consideration. One possibility is that neutrons break down into their constituent quarks, the fundamental particles that make up protons and neutrons. This would create a state of matter called quark matter, where quarks are no longer confined within individual neutrons, but exist as a vast sea of quarks, a state that might have existed in the early universe shortly after the Big Bang. Another intriguing possibility is the formation of a Bose-Einstein condensate of kaons, a type of exotic particle. In this state, a significant fraction of particles occupy the lowest quantum state, essentially behaving as a single quantum entity on a macroscopic scale. This represents yet another example of quantum mechanical effects manifesting on a stellar scale. Some theoretical models suggest that the inner core might contain strange quarks, in addition to the up and down quarks found in ordinary matter. This would form what physicists call strange quark matter, which some theories propose might be the true ground state of matter under extreme conditions. If true, this would have profound implications for our understanding of matter throughout the universe. The temperature inside a neutron star also presents a fascinating paradox. Despite initial temperatures of over 1 trillion degrees Kelvin during formation, neutron stars cool rapidly through neutrino emission. After a few 100,000 years, the temperature drops to about 1 million degrees Kelvin. Yet despite this tremendous cooling, neutron stars remain hot by human standards for millions of years, radiating primarily in X-rays. What makes this particularly interesting is that at these temperatures, any normal matter would be a plasma, a gas of charged particles. However, the extreme density inside neutron stars means that matter there is highly degenerate, with all low-energy quantum states filled. This degeneracy means that despite temperatures of millions of degrees, the interior of a neutron star behaves more like a solid or superconducting fluid, rather than a plasma. Another example of quantum effects dominating over thermal effects. The physics becomes even more extreme when we consider the effects of general relativity. The gravitational field of a neutron star is so intense that it significantly warps space-time. Near the surface, gravity is about 200 billion times stronger than Earth's gravity. This extreme curvature of space-time affects everything from the propagation of light to the ticking of clocks. One consequence of these relativistic effects is gravitational redshift. Light emitted from the surface of a neutron star loses energy as it climbs out of the gravitational well, shifting to longer wavelengths. This means that spectral lines observed from neutron stars are shifted toward the red end of the spectrum compared to the same lines measured in laboratories on Earth, an effect precisely predicted by Einstein's theory of general relativity. Time itself flows differently near a neutron star due to gravitational time dilation. If you could somehow survive on the surface of a neutron star, you would experience time passing more slowly compared to an observer far away from the star. This isn't just a theoretical curiosity. It has measurable effects on the signals we receive from neutron stars and must be accounted for in precise timing measurements of pulsars. The rotation of neutron stars introduces yet another layer of exotic physics. Conservation of angular momentum during the collapse of the progenitor star results in neutron stars spinning extremely rapidly, with rotation periods ranging from milliseconds to seconds. This rapid rotation, combined with the star's strong magnetic field, can create electric fields so powerful they tear particles from the surface and accelerate them to nearly the speed of light. The rapid rotation also causes the neutron star to bulge slightly at the equator due to centrifugal forces, deviating from a perfect sphere. For the fastest rotating neutron stars, spinning hundreds of times per second, this equatorial bulge becomes significant and affects the star's gravitational field and internal dynamics. Some neutron stars exhibit sudden increases in their rotation rate, events known as glitches. These are thought to be caused by the interaction between the neutron superfluid in the interior and the solid crust. Because the superfluid has zero viscosity, it can rotate independently of the crust. Occasionally, some of the superfluid's angular momentum is suddenly transferred to the crust, causing the observable spin rate to increase abruptly. These glitches provide valuable insights into the internal structure of neutron stars. The magnetic fields of neutron stars represent yet another arena where physics operates in extreme regimes. Typical neutron stars have magnetic fields trillions of times stronger than Earth's, and special neutron stars called magnetars can have fields thousands of times stronger still. These ultra-powerful magnetic fields affect the behavior of matter and light in profound ways. In magnetic fields, this strong quantum effects alter the behavior of atoms and molecules fundamentally. The electron orbitals in atoms become distorted, changing from their usual spherical or elliptical shapes to long, thin cylinders aligned with the magnetic field. This dramatically alters the atomic spectra and the chemical properties of elements, essentially creating an entirely different form of chemistry than what we know on Earth. Even the vacuum itself behaves differently in the presence of such extreme magnetic fields. Quantum field theory predicts that sufficiently strong magnetic fields cause the vacuum to become birefringent, meaning that light waves polarized parallel and perpendicular to the magnetic field travel at different speeds. This is a direct manifestation of quantum electrodynamics, where the vacuum is not truly empty, but filled with virtual particles that can be affected by strong fields. From the bizarre behavior of superfluids to the warping of space-time, from exotic states of quark matter to vacuum birefringence, neutron stars truly represent nature's laboratories for extreme physics. They allow us to explore regimes of density, pressure, and magnetic field strength impossible to recreate on Earth, providing crucial tests for our theories of nuclear physics, quantum mechanics, and general relativity. As we continue our cosmic journey through the night, keep in mind that these extraordinary objects, despite their extreme nature, follow the same fundamental laws of physics that govern our everyday world. They simply push these laws to their limits, revealing aspects of reality that remain hidden under ordinary circumstances. In their extremity, neutron stars offer us a glimpse of the underlying unity and elegance of the physical laws that govern our universe. Among the myriad wonders of our universe, few objects have captured the imagination of astronomers quite like pulsars. These remarkable neutron stars, spinning with clock-like precision and emitting beams of radiation that sweep through space like cosmic lighthouses, represent one of the most fascinating discoveries in the history of astronomy. Their story begins not with theoretical predictions, but with an unexpected observation that initially puzzled the scientific community. In the summer of 1967, a young graduate student named Jocelyn Bell was analyzing data from a new radio telescope she had helped build at Cambridge University. This telescope, consisting of over 2,000 dipole antennas covering an area of 4.5 acres, was designed to study quasars, distant galaxies, with incredibly bright centers. As Bell meticulously examined the miles of paper charts recording radio signals from the sky, she noticed something peculiar, a regular pattern of pulses arriving precisely every 1.33 seconds. Initially, Bell and her supervisor, Anthony Hewish, were baffled by this discovery. The remarkable regularity of the signal was unlike anything known in astronomy at that time. It was so precise that they briefly considered the possibility that they might have detected signals from an extraterrestrial civilization, whimsically dubbing the source LGM-1 for Little Green Men. However, as Bell continued her observations, she discovered 3 more sources with similar pulsing behavior, but different periods, making it unlikely that they were all signals from different alien civilizations. The true nature of these pulsing radio sources was proposed by astronomers Thomas Gold and Franco Pescini, who suggested they were rapidly rotating neutron stars. The name pulsar, a contraction of pulsating star, was coined to describe these objects. The discovery was announced in February 1968, and it was so significant that it led to the awarding of the 1974 Nobel Prize in Physics to Hewish, though controversially, Bell was not included despite her crucial role in the discovery. But what exactly makes a neutron star become a pulsar? The key lies in the combination of rapid rotation and strong magnetic fields. When a massive star collapses to form a neutron star, both its rotation rate and magnetic field are dramatically amplified due to conservation principles. The magnetic field of a neutron star, typically trillions of times stronger than Earth's, is usually not aligned with the rotation axis, similar to how Earth's magnetic field is tilted relative to its spin axis. This misalignment between the rotation and magnetic axes creates a fascinating phenomenon. The strong magnetic field accelerates charged particles, primarily electrons, to nearly the speed of light along the magnetic field lines. As these particles spiral along the curved magnetic field lines, they emit electromagnetic radiation, a process known as synchrotron radiation. This radiation is most intense along the magnetic axis, creating 2 beams of radiation emanating from the magnetic poles of the neutron star. As the neutron star rotates, these beams sweep through space like the beams from a lighthouse. If Earth happens to lie in the path of one of these beams, we observe a regular pulse of radiation each time the beam sweeps past us. This is why we detect pulsars as regular, periodic signals rather than continuous sources of radiation. It's important to note that the neutron star itself is not pulsing or changing in any way. The pulsed nature of the signal is simply a result of the rotating beam sweeping past our line of sight. The range of rotation periods observed in pulsars is remarkable. The slowest pulsars rotate about once every 10 seconds, while the fastest, known as millisecond pulsars, can spin over 700 times per second. That's faster than the blades of a kitchen blender, for an object with more mass than our Sun compressed into a 20-kilometer sphere. At such rotation rates, the equator of a neutron star is moving at a significant fraction of the speed of light. Millisecond pulsars present an interesting puzzle. Neutron stars are expected to spin rapidly when first formed, but they should gradually slow down over time as they lose rotational energy. How, then, do some pulsars attain such extraordinary rotation rates? The answer lies in binary star systems. If a neutron star has a companion star, it can gravitationally strip matter from its companion. This matter forms an accretion disk around the neutron star before falling onto its surface. As this matter spirals inward, it transfers its angular momentum to the neutron star, gradually spinning it up to rotation periods of milliseconds. This process, called recycling, effectively gives the neutron star a second life as a millisecond pulsar. Once the companion star has been completely consumed or the two stars become separated, the neutron star remains as an isolated millisecond pulsar, spinning hundreds of times per second for billions of years. The precision of pulsar rotations is truly extraordinary. Some millisecond pulsars maintain their rotation periods with a stability comparable to or exceeding the best atomic clocks on Earth. PSRB 1937 plus 21, for example, has maintained its rotation period of 1.5578 milliseconds with such precision that if measured over 100 million years, it would lose only about a third of a second. This remarkable stability makes pulsars invaluable tools for a variety of scientific purposes. One of the most significant applications of pulsar timing has been in the testing of Einstein's theory of general relativity. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, designated PSRB 1913 plus 16, consisting of a pulsar orbiting another neutron star. By precisely measuring the arrival times of the pulsar's signals over several years, they were able to determine that the orbit was slowly shrinking, exactly as predicted by general relativity due to the emission of gravitational waves. This indirect detection of gravitational waves earned Hulse and Taylor the 1993 Nobel Prize in Physics and provided one of the most stringent tests of general relativity prior to the direct detection of gravitational waves in 2015. Pulsars have also been used to confirm other predictions of general relativity, such as the Shapiro delay, where radio signals passing near a massive object are delayed due to the curvature of space-time, and the geodetic precession, where space curvature causes the axis of a rotating object to slowly change its orientation. The precision timing of pulsars has allowed astronomers to measure these effects with remarkable accuracy, consistently confirming Einstein's predictions. Beyond testing relativity, pulsars serve as cosmic clocks that allow astronomers to measure other phenomena. For instance, pulsar timing arrays, networks of precisely timed millisecond pulsars, are being used in attempts to detect the gravitational wave background of the universe, ripples in space-time caused by supermassive black hole binaries, and other massive accelerating objects throughout cosmic history. Pulsars have also enabled astronomers to make remarkable discoveries about our own cosmic neighborhood. In 1992, radio astronomers Alexander Wolszczan and Dale Frail discovered the first confirmed exoplanets, planets outside our solar system, not around a star like our Sun, but orbiting a pulsar designated PSRB 1257 plus 12. These pulsar planets were detected through tiny variations in the arrival times of the pulsar's radio pulses, caused by the pulsar's slight movement as it orbited the center of mass of the system under the gravitational influence of its planets. The discovery of pulsar planets raised fascinating questions about how planets could form or survive around these extreme stellar remnants. One possibility is that these planets formed from the debris disk left after the supernova that created the neutron star. Alternatively, they might be the remnant cores of companion stars that were nearly completely stripped by the neutron star. Either way, these worlds would be bathed in intense radiation and would represent some of the most hostile environments for any form of life as we understand it. The radio waves that led to the discovery of pulsars are just one part of the electromagnetic spectrum where these objects can be observed. Many pulsars also emit pulses in visible light, X-rays, and gamma rays. The Crab pulsar, the central neutron star in the Crab Nebula is one of the few pulsars that can be observed across the entire electromagnetic spectrum, from radio waves to gamma rays. This particular pulsar, formed in a supernova observed by Chinese astronomers in 1054 CE, rotates about 30 times per second and is one of the most studied objects in the night sky. Each pulse from a pulsar has a characteristic shape and polarization that provides valuable information about the neutron star's magnetic field and the surrounding plasma environment. Interestingly, the radio pulses from individual rotations can vary significantly in intensity, a phenomenon known as pulse-to-pulse variation. Some pulsars even exhibit nulling, where they seem to turn off for several pulse periods before resuming their regular emission. Perhaps even more intriguing are the glitches observed in some pulsars. Normally, pulsars slow down very gradually as they lose rotational energy. However, occasionally a pulsar will suddenly spin up, increasing its rotation rate by a tiny fraction. These glitches are thought to be caused by sudden transfers of angular momentum from the superfluid interior to the solid crust of the neutron star, providing a rare glimpse into the internal dynamics of these extreme objects. Over time, pulsars gradually slow their rotation as they radiate energy. This slowdown, measured as the rate of change of the pulse period, allows astronomers to estimate the age of pulsars. Typically, normal pulsars have lifetimes of about 10 to 100 million years before they slow down to the point where they no longer emit detectable radiation. Millisecond pulsars, having been recycled through accretion, can remain active for billions of years due to their lower energy loss rates. The study of pulsars has also led to unexpected discoveries about the interstellar medium, the gas and dust between stars. As radio waves from pulsars travel through this medium, they interact with free electrons, causing different frequencies to travel at slightly different speeds, a phenomenon known as dispersion. By measuring this dispersion, astronomers can determine the density of electrons along the line of sight, effectively using pulsars as probes of the interstellar medium. Another fascinating phenomenon observed in some pulsars is known as scintillation, where the intensity of the radio signal fluctuates due to interference patterns created as the radio waves pass through irregularities in the interstellar medium. This is similar to the twinkling of stars caused by Earth's atmosphere, but occurs on much larger scales across interstellar distances. By studying these scintillation patterns, astronomers can investigate the turbulent properties of the interstellar gas. To date, astronomers have discovered more than 3,000 pulsars in our galaxy, with more being found each year as survey sensitivities improve. However, these represent only a small fraction of the estimated 1 billion neutron stars in the Milky Way. Most neutron stars are simply undetectable because their emission beams never sweep across Earth, or because they have slowed down to the point where they no longer generate the conditions necessary for pulsar emission. As we contemplate these remarkable cosmic lighthouses, spinning with incredible precision and beaming radiation across the vastness of space, we are reminded of the extraordinary physics at work in our universe. From the quantum mechanical processes accelerating particles, to relativistic speeds, to the macroscopic dynamics of rotating stellar remnants, pulsars embody the fascinating interplay between the very small and the very large that characterizes modern physics. In the silent depths of space, these stellar beacons continue their metronomic rotations, marking time with a precision that rivals our best terrestrial clocks. As their beams sweep through the darkness, they not only illuminate our understanding of extreme physics, but also serve as tools to probe everything from the fabric of space-time to the tenuous gas between stars. Truly, pulsars stand as one of nature's most extraordinary achievements, cosmic lighthouses guiding us toward deeper insights into the fundamental workings of our universe. In the pantheon of extreme cosmic objects, magnetars stand out as particularly extraordinary. These rare and enigmatic neutron stars possess magnetic fields of such overwhelming strength that they defy imagination and push the boundaries of known physics. While ordinary neutron stars already feature magnetic fields trillions of times stronger than Earth's, magnetars amplify this to an entirely different level, harboring fields thousands of times more powerful still. In these cosmic monsters, magnetism reigns supreme, dominating their behavior and creating some of the most violent phenomena observed in our galaxy. The story of magnetars began in March 1979, when an unexpected burst of gamma rays was detected by several spacecraft designed to monitor nuclear weapons tests. This burst, originating from a point in the constellation Dorado, was so intense that it saturated the detectors despite coming from a source outside our solar system. The radiation was strong enough to ionize Earth's upper atmosphere, and the event was followed by a gradually fading emission of X-rays that pulsed with a period of 8 seconds, suggesting a rotating neutron star as the source. Several similar events were observed in the following decades, but it wasn't until the 1990s that astronomers Robert Duncan and Christopher Thompson proposed a theoretical framework to explain these observations. They suggested the existence of neutron stars with magnetic fields hundreds to thousands of times stronger than typical neutron stars, with field strengths reaching 1 quadrillion Gauss. For comparison, Earth's magnetic field is about 1/2 Gauss, and a strong refrigerator magnet might be 100 Gauss. These extreme magnetic fields would be powerful enough to produce the observed giant flares of gamma rays. Thus, the concept of the magnetar was born. To understand how such extraordinary magnetic fields could arise, we need to consider the conditions during a neutron star's formation. When the core of a massive star collapses during a supernova, the conservation of magnetic flux ensures that the initial magnetic field of the star is amplified as the core shrinks. But this mechanism alone isn't sufficient to explain the extreme fields of magnetars. Duncan and Thompson proposed an additional process called a dynamo mechanism, which could operate during the first few seconds after the neutron star's birth. During this brief window, if the newborn neutron star is rotating very rapidly, making a complete turn in under 3 milliseconds, convective motions in the hot, differentially rotating interior can amplify the magnetic field dramatically through a process similar to how Earth's magnetic field is generated, but operating on a much faster and more extreme scale. This dynamo action can boost the field strength to the extraordinary levels observed in magnetars. The magnetic fields of magnetars are so intense that they literally affect the structure of matter and even empty space itself. In fields of this strength, atoms are distorted into elongated, needle-like shapes, rendering conventional chemistry impossible. Molecular bonds that would form under normal conditions are prevented from forming, and entirely new types of bonds become possible. The vacuum itself becomes birefringent, meaning that light waves oscillating in different directions travel at different speeds, a direct consequence of quantum electrodynamics that can only be observed in such extreme conditions. Perhaps the most dramatic manifestations of magnetars are the giant flares they occasionally produce. These cataclysmic events can release more energy in 1/10 of a second than our sun emits in 100,000 years. The flare detected in 1979, which first alerted astronomers to these bizarre objects, released approximately 10 to the 44 ergs of energy, primarily in the form of gamma rays. A similar event from SGR 180620 on December 27, 2004 was so powerful that it measurably affected Earth's upper atmosphere, despite originating from a magnetar approximately 50,000 light-years away on the other side of our galaxy. These giant flares are thought to be caused by massive rearrangements of the magnetic field, analogous to solar flares, but far more powerful. The immense magnetic stress builds up as the field lines become twisted and tangled, eventually leading to a catastrophic reconfiguration of the field, releasing enormous amounts of energy in the process. This energy powers a fireball of plasma that expands at relativistic speeds, emitting the observed burst of gamma rays. Following these major eruptions, magnetars often exhibit a distinct pattern. The initial spike of gamma rays lasting less than a second, followed by a longer emission that fades over minutes, pulsating with the rotation period of the magnetar. This pulsating tail is thought to be caused by a trapped fireball, a cloud of hot plasma confined by the strong magnetic field near the magnetar's surface. As the magnetar rotates, different portions of this confined fireball become visible, creating the observed pulsations. Beyond these spectacular flares, magnetars also experience more frequent, less energetic bursts and persistent X-ray emission. The persistent emission is thought to be powered by the decay of the magnetic field itself. As the incredibly strong field gradually weakens, it releases energy that heats the magnetar's surface to temperatures of about 10 million degrees Kelvin, causing it to glow brightly in X-rays. This magnetic field decay provides an internal heating source that keeps magnetars hotter and more luminous than ordinary neutron stars of similar age. The surface of a magnetar presents a truly alien landscape. The intense magnetic field affects the transport of heat, creating temperature variations across the surface that may differ by millions of degrees. The crust, a solid lattice of atomic nuclei, is under immense stress from both the gravitational and magnetic forces. This stress can occasionally exceed the breaking strength of the crust, resulting in a starquake, a sudden fracture and rearrangement of the crust that can trigger the bursts of radiation observed from magnetars. These starquakes can be truly monumental events. The energy released in a major magnetar starquake might be equivalent to a magnitude 32 earthquake on the Richter scale, compared to the largest recorded earthquakes on Earth, which reach only about magnitude 9. During such events, the entire crust of the neutron star may shift and crack, releasing tremendous amounts of energy and possibly ejecting particles at nearly the speed of light. Beyond their dramatic flares and bursts, magnetars also exhibit more subtle but equally fascinating behaviors. Their rotation gradually slows down over time, as is common for neutron stars, but magnetars show much more irregular spin-down behavior than ordinary pulsars. They frequently exhibit glitches, sudden increases in rotation rate, as well as anti-glitches, unexpected decreases in rotation rate. These changes in spin behavior are thought to be connected to the evolution of the magnetic field and its interaction with the neutron star's interior. Intriguingly, magnetars also display variations in their pulse profiles, the shape of the periodic signals we receive as they rotate. These variations suggest that the magnetic field configuration is not static, but evolves over time. The pulse profiles can change dramatically after major flares, indicating significant restructuring of the magnetic field or the neutron star's surface following these energetic events. To date, astronomers have confirmed approximately 30 magnetars in our galaxy, making them quite rare compared to the total neutron star population of roughly 1 billion. However, this observed rarity might be partly due to selection effects. Magnetars are typically detected through their X-ray emission or bursting activity, which may only be observable during a relatively brief period of their lives, perhaps a few thousand to 100,000 years. After this active phase, as their magnetic fields decay and they cool, they might become indistinguishable from ordinary neutron stars. This leads to an intriguing possibility. Magnetars might not be an entirely separate class of neutron stars, but rather a phase in the life cycle of some neutron stars. Perhaps a significant fraction of neutron stars begin their lives as magnetars, but are only observable as such during their youth when their magnetic fields are strongest. Supporting this idea, some relatively young neutron stars exhibit properties intermediate between typical pulsars and magnetars, suggesting a potential evolutionary link. The study of magnetars provides valuable insights into the behavior of matter and energy under conditions impossible to recreate in terrestrial laboratories. The magnetic fields of magnetars are thousands of times stronger than anything we can create on Earth, offering a unique window into extreme physics. These fields are strong enough to affect quantum electrodynamics, the theory that describes how light interacts with matter, allowing astronomers to test this fundamental theory under the most extreme conditions. For instance, in magnetic fields as strong as those of magnetars, virtual particles that normally flicker in and out of existence in the quantum vacuum can be affected, leading to phenomena such as photon splitting, where a single photon divides into two lower energy photons, and vacuum birefringence, where the vacuum itself becomes polarized. These exotic quantum effects, predicted by theory but difficult to observe under normal conditions, may be detectable in the radiation from magnetars. Magnetars also provide insights into the equation of state of neutron star matter, the relationship between pressure and density in the incredibly compressed material of a neutron star. The strong magnetic fields of magnetars can deform the star, making it slightly non-spherical. The degree of this deformation depends on the stiffness of the neutron star material, which in turn depends on its composition and the behavior of matter at nuclear densities. By studying magnetars, astronomers can constrain the properties of matter under conditions that cannot be replicated in laboratories. Beyond their significance for fundamental physics, magnetars may play important roles in various astrophysical phenomena. Some researchers have proposed that magnetars could be the engines powering certain types of gamma-ray bursts, particularly the shorter variety lasting less than 2 seconds. These catastrophic cosmic explosions, visible across billions of light years, might be triggered by the formation or sudden collapse of a magnetar. Magnetars have also been suggested as potential sources of fast radio bursts, mysterious millisecond-long flashes of radio waves detected from distant galaxies. The first repeating fast radio burst source, FRB 12102, shows properties consistent with a young magnetar in a distant galaxy. While this connection is still being investigated, it highlights the potential role of magnetars in some of the most enigmatic phenomena in modern astronomy. The study of magnetars faces significant challenges due to their rarity and the unpredictable nature of their bursting activity. Most known magnetars are located in the plane of our galaxy, where dust and gas can obscure our view, particularly at wavelengths other than X-rays and gamma rays. This makes multi-wavelength studies difficult, limiting our ability to understand these objects comprehensively. Despite these challenges, our understanding of magnetars has advanced significantly in recent decades, thanks to dedicated X-ray observatories such as NASA's Swift and Fermi satellites, and the European Space Agency's XMM Neutron. These observatories have allowed astronomers to catch magnetars in the act of bursting and to study their persistent emission in detail, revealing new insights into their behavior and evolution. The discovery of magnetars has fundamentally changed our understanding of neutron stars and the extremes of physics. Before their theoretical prediction and subsequent observation, few would have imagined that such extreme magnetic fields could exist in nature. Their study continues to challenge our understanding of nuclear physics, quantum electrodynamics, and the behavior of matter under the most extreme conditions the universe has to offer. As we gaze up at the night sky, consider that among the countless stellar points of light, there exist these cosmic magnetic monsters, silently harboring magnetic fields of unimaginable strength, occasionally announcing their presence with eruptions of energy that momentarily outshine entire galaxies. In their quiet rotation and their catastrophic flares, magnetars remind us of the extraordinary diversity of objects that populate our universe and the extreme conditions under which the laws of physics must still apply. The study of these enigmatic objects continues to be a vibrant area of research in modern astrophysics, with each new observation bringing fresh insights and often new puzzles. As our observational capabilities advance, we can look forward to unveiling more of the secrets of these cosmic magnetic powerhouses, furthering our understanding of the most extreme objects in the cosmos and the fundamental laws that govern them. In the cosmic dance of stars that fills our galaxy, some partners perform a particularly captivating and ultimately fatal waltz. Binary neutron star systems, where two of the densest objects in the universe orbit one another in an ever-tightening embrace, represent some of the most fascinating and informative laboratories for extreme physics. Their orbital evolution, culminating in cataclysmic mergers, not only tests our understanding of gravity to its limits, but also creates the conditions for forging the heaviest elements in the periodic table. These systems connect the microscopic world of nuclear physics with the macroscopic realm of cosmic evolution, linking the smallest particles to the grandest structures in the universe. The story of binary neutron stars begins with their progenitors, massive binary star systems. In such systems, two stars much more massive than our Sun orbit their common center of mass. These stellar behemoths evolve more rapidly than smaller stars, exhausting their nuclear fuel and reaching the ends of their lives within tens of millions of years. For a binary neutron star system to form, both stars must be massive enough to eventually collapse into neutron stars, typically requiring original masses between 8 and 20 times that of our Sun. The evolution of such massive binary systems follows a complex path. Usually, the more massive star evolves faster, swelling into a red supergiant before exploding as a supernova and leaving behind a neutron star. This first supernova is a critical juncture for the binary system. The explosion itself is rarely perfectly symmetric, and the resulting kick can potentially disrupt the binary, sending the newly formed neutron star and its companion on separate trajectories through the galaxy. For a binary neutron star system to form, this first supernova must leave the binary intact, which occurs in only a minority of cases. If the binary survives the first supernova, the second star eventually follows a similar evolutionary path, exploding and leaving behind a second neutron star. Again, this supernova can potentially disrupt the system, and many binaries do not survive this second explosion. The small fraction that remain bound become the binary neutron star systems that astronomers observe today. These systems are therefore relatively rare, with only about 20 confirmed examples known in our galaxy. Once formed, a binary neutron star system consists of two incredibly dense objects, each containing more mass than our Sun, compressed into a sphere roughly 20 kilometers in diameter, orbiting their common center of mass. Initially, these orbits may be quite wide, with orbital periods of hours or days, and separations of hundreds of thousands or millions of kilometers. However, unlike planetary orbits in our solar system, which remain stable for billions of years, the orbits of binary neutron stars gradually decay over time. The mechanism behind this orbital decay was predicted by Albert Einstein's general theory of relativity. According to Einstein, accelerating masses should produce ripples in the fabric of space-time itself, carrying away energy and momentum. These ripples, called gravitational waves, travel at the speed of light and cause the binary system to lose orbital energy, resulting in the neutron stars spiraling closer together. As they do so, their orbital period decreases and they move faster and faster around their common center of mass. The first indirect evidence for this process came from a binary pulsar system discovered in 1974 by radio astronomers Russell Hulse and Joseph Taylor. This system, designated PSRB 1913+16, consists of a pulsar orbiting another neutron star with a period of about 7 3/4 hours. By precisely timing the radio pulses from the pulsar over several years, Hulse and Taylor observed that the orbital period was decreasing at exactly the rate predicted by general relativity due to the emission of gravitational waves. This remarkable confirmation of Einstein's theory earned them the 1993 Nobel Prize in Physics. As binary neutron stars spiral closer together, the rate at which they emit gravitational waves increases dramatically. The power emitted in gravitational waves is proportional to the fifth power of the orbital velocity, which means that the system emits more and more gravitational wave energy as the neutron stars approach each other. In the final minutes before merger, the power emitted in gravitational waves can exceed the combined electromagnetic output of all the stars in the observable universe. During this final in-spiral phase, the neutron stars orbit each other hundreds of times per second, moving at significant fractions of the speed of light. The gravitational waves emitted during this phase have frequencies in the range of tens to hundreds of hertz, making them potentially detectable by ground-based gravitational wave observatories such as LIGO, the Laser Interferometer Gravitational Wave Observatory, and its European counterpart, Virgo. The first direct detection of gravitational waves from a binary neutron-star merger came on August 17, 2017, when the LIGO and Virgo detectors observed a signal designated GW170817. This signal, lasting approximately 100 seconds, showed the characteristic chirp of gravitational waves as the frequency and amplitude increased when the neutron stars spiraled closer together. The signal abruptly ended when the neutron stars collided, approximately 130 million light-years from Earth in the galaxy NGC 4993 in the Hydra constellation. What made this event particularly groundbreaking was that, unlike previous gravitational wave detections from black hole mergers, this neutron-star collision was also observed across the electromagnetic spectrum. Just 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same direction. This was followed by observations in X-rays, ultraviolet, optical, infrared, and radio wavelengths by dozens of observatories around the world and in space. This marked the beginning of the era of multi-messenger astronomy, where cosmic events are studied through multiple channels of information: gravitational waves, electromagnetic radiation, and potentially neutrinos. The observations of GW170817 provided a wealth of scientific insights. The gravitational wave signal allowed astronomers to measure the masses of the neutron stars, finding them to be about 1.4 and 1.1 times the mass of our Sun, respectively. The detection across multiple observatories helped precisely locate the source galaxy and provided evidence for a long-held theory that short gamma-ray bursts are produced by neutron-star mergers. But perhaps the most profound implication came from the optical and infrared observations that followed. As the debris from the merger expanded and cooled, it glowed with a particular reddish light that matched theoretical predictions for a process called the R process, or Rapid Neutron Capture Process. This process, first proposed in the 1950s, is a sequence of nuclear reactions in which atomic nuclei rapidly capture neutrons to form heavier elements. It requires an environment with an extremely high density of free neutrons, conditions that are difficult to find in the universe. The observations of the kilonova, as the optical counterpart to the neutron-star merger is called, provided strong evidence that neutron-star mergers are a primary site for the R process. This process is responsible for creating many of the heaviest elements in the periodic table, including gold, platinum, uranium, and about half of all elements heavier than iron. The spectroscopic data from the kilonova showed the signatures of these newly formed heavy elements being ejected into space at about 1/5 the speed of light. This remarkable discovery connected the cosmic cataclysm of neutron-star mergers to the origin of the precious metals we value on Earth. The gold in your jewelry, the platinum in catalytic converters, and the uranium that powers nuclear reactors were all likely forged in the fiery aftermath of neutron-star collisions billions of years ago. These elements were then incorporated into the molecular cloud that eventually formed our solar system and ultimately became part of our planet and ourselves. As the astronomer Carl Sagan once said, we are literally made of star stuff. And in the case of many heavy elements, specifically neutron star stuff, the merger of two neutron stars can result in different outcomes depending on the total mass involved and the equation of state of nuclear matter, which describes how matter behaves at the extreme densities found in neutron stars. If the combined mass exceeds a certain threshold, known as the Tolman-Oppenheimer-Volkoff limit, the remnant will collapse directly into a black hole. If the mass is below this limit, the result might be a more massive neutron star. In many cases, the merger initially forms a hypermassive neutron star, an object temporarily supported against gravitational collapse by its rapid rotation. As this rotation slows due to various braking mechanisms, the support weakens, and the hypermassive neutron star eventually collapses into a black hole, typically within seconds to minutes after the merger. During its brief existence, this hypermassive neutron star can emit strong electromagnetic radiation, potentially explaining some of the features observed in gamma-ray bursts. The neutron-rich material ejected during the merger undergoes the R process, nucleosynthesis, mentioned earlier. Some of this material is thrown out directly during the collision in what is called dynamical ejector. Additional material may be ejected from the accretion disk that forms around the remnant through processes driven by neutrino heating and magnetic fields. This ejected material, enriched with newly formed heavy elements, expands into the surrounding space, eventually mixing with the interstellar medium. Over cosmic time, many such events have contributed to the chemical enrichment of galaxies, including our own Milky Way. Binary neutron star systems also serve as excellent laboratories for testing theories of gravity. According to general relativity, gravitation is a manifestation of the curvature of space-time caused by mass and energy. Alternative theories of gravity often predict deviations from Einstein's theory that would be most noticeable in strong gravitational fields, exactly the conditions found in neutron star binaries. By precisely measuring the orbital decay of these systems and the gravitational waves they emit, astronomers can test general relativity to high precision and constrain or rule out alternative theories. For example, some alternative theories predict that gravitational waves might travel at speeds different from the speed of light, or might have additional polarization states beyond the two predicted by general relativity. The near-simultaneous arrival of gravitational waves and gamma rays from GW 170817 constrained the difference in speed between gravity and light to less than 1 part in 10 to the 15th. This remarkably precise measurement eliminated many alternative theories of gravity that had been proposed. The study of binary neutron stars also provides unique insights into the properties of neutron stars themselves. The gravitational wave signal from a merger contains information about how the neutron stars deform as they approach each other, which depends on their internal structure. This in turn constrains the equation of state of nuclear matter, helping physicists understand how matter behaves at densities several times greater than that of an atomic nucleus, conditions impossible to create in terrestrial laboratories. The future of binary neutron star research looks exceptionally promising. Gravitational wave observatories are continuously improving their sensitivity, which will allow them to detect neutron star mergers from greater distances and with greater precision. As more events are observed, astronomers will build a statistical picture of the neutron star merger rate and the properties of these systems. This information will shed light on the formation and evolution of binary stars, nucleosynthesis of heavy elements, and the expansion rate of the universe. The detection of gravitational waves from neutron star mergers has also opened a new avenue for measuring the expansion rate of the universe, a value known as the Hubble constant. By combining the distance information from the gravitational wave signal with the redshift of the host galaxy, astronomers can make an independent measurement of this fundamental cosmological parameter. As more neutron star mergers are detected, this approach may help resolve the current tension between different methods of measuring the Hubble constant, one of the most significant puzzles in modern cosmology. Beyond individual binary neutron star systems, astronomers are also searching for a background of gravitational waves produced by the combined effect of many distant, unresolved binary systems throughout the universe. This gravitational wave background would contain information about the cosmic history of neutron star formation and evolution. Detection of this background would require precise timing of many millisecond pulsars, using them as a galaxy-scale gravitational wave detector in what is called a pulsar timing array. In addition to their enormous scientific value, binary neutron stars and their mergers capture the imagination because they connect the vastness of the cosmos with the intimate details of our existence. The heavy elements created in these mergers are essential components of our technology, our planet, and even our bodies. Every gold atom in your jewelry was likely forged in the fiery aftermath of colliding neutron stars, the alchemy of the cosmos transforming nuclear matter into precious metal. As we gaze at the night sky, Contemplating the countless stars scattered across the darkness, consider that among them are these binary systems, these cosmic harbingers of creation through destruction. In their slow dance and violent collision, they exemplify the universe's cycle of transformation, where even the most catastrophic events lead to the creation of new possibilities. From the merger of neutron stars come the building blocks of planets and life, a cosmic reminder that endings often herald new beginnings, that destruction and creation are two sides of the same universal coin. In the grand cosmic perspective, these binary neutron stars and their mergers represent nature's most extreme laboratory, where the fundamental forces of the universe interact to create the conditions necessary for complexity and diversity. Through their study, we glimpse the profound interconnectedness of the cosmos, from the smallest subatomic particles to the largest structures, from the earliest moments of the universe to the precious metals adorning our world today. They remind us that we are indeed children of the stars, connected through time and space to some of the most energetic events the universe has to offer. Chapter 6. The role of neutron stars in the universe. In the grand cosmic tapestry, neutron stars occupy a unique and significant position. Far from being mere celestial oddities or the dormant remnants of stellar evolution, these extraordinary objects play crucial roles in the physics, chemistry, and evolution of our universe, from serving as cosmic laboratories for extreme physics to influencing galactic evolution and creating the conditions necessary for the synthesis of heavy elements. Neutron stars are active participants in the ongoing cosmic story. Their influence extends from the subatomic scale to the grandest cosmic structures, connecting phenomena across vast differences in scale and energy. Perhaps the most profound role of neutron stars is as natural laboratories for physics under extreme conditions. The densities, pressures, magnetic fields, and gravitational fields found in and around neutron stars far exceed anything we can create in terrestrial experiments. This makes neutron stars invaluable tools for testing theories and exploring phenomena that would otherwise remain in the realm of pure theory. At the core of neutron stars, matter exists at densities of up to 10 to the 15th grams per cubic centimeter, exceeding the density of atomic nuclei. Under such conditions, the boundaries between nuclear and particle physics blur, and exotic states of matter may form. By studying neutron stars, physicists can constrain the equation of state of ultra-dense matter, which describes how pressure relates to density under these extreme conditions. This equation of state remains one of the greatest unsolved problems in nuclear physics, with implications for our understanding of the strong nuclear force and quantum chromodynamics, the theory of how quarks and gluons interact. The extreme gravitational fields of neutron stars, with surface gravity approximately 100 billion times stronger than Earth's, provide natural laboratories for testing Einstein's general theory of relativity. The first indirect detection of gravitational waves came from observing the orbital decay of a binary pulsar system, confirming Einstein's prediction that accelerating masses should emit ripples in space-time. More recently, the direct detection of gravitational waves from neutron star mergers has provided some of the most stringent tests of general relativity to date. These observations have confirmed that gravitational waves travel at the speed of light and have placed tight constraints on alternative theories of gravity. The ultra-strong magnetic fields of magnetars, which can reach up to 10 to the 15th Gauss, allow astronomers to probe quantum electrodynamics, the theory of how light and matter interact under conditions impossible to create on Earth. In magnetic fields this strong, the vacuum itself becomes birefringent, meaning that light waves polarized in different directions travel at different speeds. This effect, called vacuum birefringence, was predicted by quantum electrodynamics decades ago, but has only recently been observed in the light from neutron stars. Such observations provide crucial tests of quantum field theory in extreme regimes. Beyond their role as physics laboratories, neutron stars significantly influence the evolution and dynamics of their host galaxies. Though small in size, their influence extends far beyond their immediate vicinity, affecting processes on galactic scales. One way neutron stars impact galactic evolution is through their supernova births. The explosive deaths of massive stars that create neutron stars release tremendous amounts of energy and newly synthesized elements into the interstellar medium. These explosions can trigger the formation of new stars by compressing nearby gas clouds, and they enrich the galactic medium with elements heavier than hydrogen and helium, which are essential for the formation of planets and eventually life. The shock waves from these supernovae also help maintain the turbulence in the interstellar medium that plays a crucial role in regulating star formation throughout the galaxy. Neutron stars also influence their surroundings through powerful outflows of energy and particles. Pulsars, with their regularly pulsating beams of radiation, inject enormous amounts of energy into their surroundings in the form of relativistic particles and electromagnetic radiation. These outflows create pulsar wind nebulae, expanding bubbles of high-energy particles and magnetic fields that can span several light years. The most famous example is the Crab Nebula, powered by a central pulsar that was formed in a supernova observed by Chinese astronomers in 1054 CE. This pulsar converts its rotational energy into a wind of particles and radiation so powerful that it causes the entire nebula to glow across the electromagnetic spectrum. These pulsar wind nebulae serve as cosmic particle accelerators, boosting electrons and positrons to energies far higher than those achievable in human-built particle accelerators like the Large Hadron Collider. As these particles diffuse through the galaxy, they contribute to the cosmic ray population, affecting the ionization state and chemistry of the interstellar medium. Some cosmic rays eventually reach Earth, where they interact with our atmosphere to produce showers of secondary particles that can be detected on the ground. In this way, distant neutron stars influence phenomena that occur in our immediate terrestrial environment. Millisecond pulsars, neutron stars that have been spun up to rotation periods of just a few milliseconds by accreting matter from a companion star, play a unique role in the dynamics of globular clusters. These ancient, densely packed clusters of stars contain relatively large numbers of millisecond pulsars. The presence of these pulsars helps astronomers understand the complex gravitational interactions in these crowded stellar environments and provides insights into how binary star systems form and evolve in places where stars are separated by distances not much greater than the distance between Earth and the Sun. Among the most significant roles neutron stars play in the cosmos is their contribution to nucleosynthesis, the creation of chemical elements. While most elements up to iron can be produced through nuclear fusion in the cores of regular stars, the synthesis of heavier elements requires different processes. As we explored in the previous chapter, neutron star mergers provide the ideal environment for the R process, or rapid neutron capture process, which creates approximately half of all elements heavier than iron, including gold, platinum, and uranium. The discovery of the electromagnetic counterpart to the gravitational wave event GW 170817 provided direct observational evidence that neutron star mergers produce these heavy elements. The kilonova, the optical and infrared glow that followed the merger, displayed spectral signatures consistent with the production and presence of freshly synthesized heavy elements. This confirmed a theoretical prediction that had stood for decades without direct observational evidence. The role of neutron stars in creating heavy elements connects these exotic objects directly to our daily lives. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, and even elements like iodine that are essential for human health, may have been forged in neutron star mergers billions of years ago before becoming incorporated into the molecular cloud that eventually formed our solar system. In a very real sense, we carry the products of neutron star collisions with us every day. Neutron stars also serve as sources of some of the most energetic phenomena in the universe. Magnetars, with their colossal magnetic fields, can produce giant flares that briefly outshine all other gamma-ray sources in the sky combined. A particularly powerful flare from the magnetar SGR 180620 in 2004 produced measurable effects on Earth's ionosphere despite originating from the other side of our galaxy, 50,000 light-years away. Neutron stars are also leading candidates for the engines powering certain types of gamma-ray bursts, particularly short gamma-ray bursts lasting less than about 2 seconds. The gravitational wave event GW 170817 provided the first direct confirmation of this connection, showing a short gamma-ray burst occurring just 1.7 seconds after the merger of 2 neutron stars. These gamma-ray bursts are among the most energetic events in the universe since the Big Bang, releasing in a few seconds as much energy as our Sun will produce in its entire 10 billion-year lifetime. The role of neutron stars extends to serving as cosmic clocks. Pulsars, particularly millisecond pulsars, rotate with remarkable regularity, rivaling the precision of atomic clocks on Earth. This rotational stability makes them valuable tools for a variety of scientific purposes. Networks of precisely timed pulsars, known as pulsar timing arrays, can function as galaxy-scale gravitational wave detectors, sensitive to the low-frequency gravitational waves produced by supermassive black hole binaries and other massive systems. Pulsars also provide a means to test Einstein's general relativity and alternative theories of gravity. The Hulse-Taylor binary pulsar and similar systems have confirmed the existence of gravitational waves through their orbital decay. Other pulsar systems have allowed astronomers to test the strong equivalence principle, which states that the gravitational effects of a body's composition should be undetectable, and to look for variations in the gravitational constant over time, a prediction of some alternative theories of gravity. Some pulsars also serve as cosmic compasses. The very regular pulses from millisecond pulsars can be used as navigation beacons for spacecraft. NASA has developed the concept of X-ray pulsar navigation, which would allow spacecraft to determine their position in the solar system by timing the arrival of X-ray pulses from multiple pulsars, a cosmic version of the global positioning system. This could enable autonomous navigation in deep space, reducing the need for communication with Earth. Neutron stars also play a crucial role in the study of dark matter, the mysterious substance that makes up about 85% of the matter in the universe, but does not interact with light. Some theories predict that dark matter particles could accumulate in the intense gravitational fields of neutron stars, potentially leading to observable effects. For example, if dark matter particles are their own antiparticles, they might annihilate each other inside neutron stars, producing additional heat that could be detected as increased thermal emission. By measuring the temperatures of old neutron stars, astronomers can place constraints on the properties of dark matter particles. The cooling of neutron stars over time provides insights into the physics of superfluidity and superconductivity. The interior of a neutron star is predicted to contain superfluid neutrons and superconducting protons, quantum states of matter where particles flow without resistance. These exotic states affect how the neutron star cools over time, and by observing this cooling, astronomers can test theories of superfluidity and superconductivity under extreme conditions. This connects the macroscopic behavior of neutron stars to quantum phenomena usually observed only at temperatures near absolute zero in laboratory settings. In recent years, fast radio bursts, mysterious millisecond-long flashes of radio waves, have emerged as one of the most intriguing puzzles in astronomy. Some of these bursts have been associated with magnetars, suggesting that at least a subset of fast radio bursts may be produced by these highly magnetized neutron stars. The discovery of a fast radio burst from the galactic magnetar, SGR 1935+2-154, in 2020 provided strong evidence for this connection. Understanding the mechanism behind these bursts could reveal new aspects of plasma physics and the behavior of matter in ultra-strong magnetic fields. Neutron stars also contribute to our understanding of stellar evolution and the final stages of massive stars. By studying the population of neutron stars in our galaxy, their masses, rotation rates, and magnetic fields, astronomers can refine theories of how massive stars evolve and explode as supernovae. Questions such as which stars form neutron stars versus black holes, how much mass is lost during the supernova explosion, and how the rotation and magnetic field of the progenitor star translate to those of the resulting neutron star, can all be addressed by comprehensive studies of neutron star populations. The existence of neutron stars in binary systems with regular stars, known as high-mass X-ray binaries, provides windows into the evolution of binary star systems. In these systems, matter from the companion star falls onto the neutron star, heating up to millions of degrees and emitting X-rays. By studying the properties of these systems, astronomers can understand how binaries evolve through various stages, including common envelope phases where one star engulfs its companion, and mass transfer episodes that can drastically change the properties of both stars. Looking to the future, neutron stars will continue to play pivotal roles in advancing our understanding of fundamental physics and the universe. As gravitational wave observatories improve their sensitivity, many more neutron star mergers will be detected, providing a wealth of data on the equation of state of dense matter, the cosmic rate of heavy element production, and the expansion rate of the universe. Space-based X-ray observatories will provide ever more detailed views of the surfaces and surroundings of neutron stars, potentially revealing direct evidence of exotic states of matter or the effects of quantum gravity. In the grand tapestry of the cosmos, neutron stars stand as remarkable threads, connecting seemingly disparate aspects of the universe. From the quantum mechanical behavior of subatomic particles to the synthesis of elements essential for life, from the warping of space-time predicted by general relativity to the generation of the most powerful explosions since the Big Bang, neutron stars touch upon virtually every aspect of astrophysics. They remind us that even these remnants of stellar deaths continue to shape and influence the universe in profound ways, participating actively in the cosmic story that began billions of years ago and continues to unfold around us. As we contemplate these extraordinary objects, we are reminded of the interconnectedness of all things in the cosmos. The matter in our bodies, the gold in our jewelry, the very ground beneath our feet, all bear the imprint of processes that have occurred throughout cosmic history, including those involving neutron stars. Far from being distant and irrelevant curiosities, these extreme objects are intimately connected to our existence, part of the grand cosmic cycle that transforms matter and energy throughout the universe, creating the conditions necessary for stars, planets, and eventually life itself. The observation of neutron stars presents astronomers with unique challenges and opportunities. These extraordinary objects, despite their extreme nature, are remarkably difficult to detect directly. A typical neutron star spans a mere 20 kilometers in diameter, yet might be located thousands of light years away. At such distances, resolving a neutron star as more than a point of light requires angular resolution far beyond what current telescopes can achieve. Yet through ingenuity, technological innovation, and a multi-wavelength approach, astronomers have developed sophisticated methods to study these elusive stellar remnants across the electromagnetic spectrum and beyond, gleaning crucial information about their properties and behavior. The story of neutron star observation begins with radio astronomy. In 1967, Jocelyn Bell, then a graduate student working with her advisor Anthony Hewish at Cambridge University, noticed a series of remarkably regular pulses in the data from their radio telescope. The source, initially nicknamed LGM1 for Little Green Men due to the clockwork regularity that momentarily suggested an artificial origin, was soon recognized as a rapidly rotating neutron star, or pulsar. This groundbreaking discovery, made using a relatively simple radio telescope consisting of dipole antennas spread across several acres, opened the door to the study of neutron stars. Radio observations remain a cornerstone of neutron star astronomy. Modern radio telescopes, such as the Arecibo Observatory before its unfortunate collapse in 2020, the Green Bank Telescope in West Virginia, the Parkes Observatory in Australia, and the more recently constructed 500-meter aperture spherical telescope in China have discovered thousands of pulsars. These discoveries were made possible by conducting systematic sky surveys in which astronomers scan large portions of the sky looking for the distinctive periodic signals that characterize pulsars. Radio observations provide crucial information about neutron stars. The period of the pulses reveals the rotation rate of the neutron star, while changes in this period over time indicate how rapidly the neutron star is slowing down due to energy loss. This spin-down rate, in turn, allows astronomers to estimate the strength of the neutron star's magnetic field and its age. Radio astronomers can also measure the dispersion of the pulsar signal, the slight delay in the arrival time of different radio frequencies caused by their passage through the interstellar medium. This dispersion serves as a measure of the amount of ionized gas between Earth and the pulsar, providing information about the structure of our galaxy. One of the most powerful techniques in radio astronomy for studying pulsars is pulsar timing. By precisely measuring the arrival times of pulses over months and years, astronomers can determine the pulsar's position in the sky, its proper motion, and even detect the presence of planets orbiting the neutron star. For pulsars in binary systems, timing can reveal the mass of both the pulsar and its companion, as well as orbital parameters, such as eccentricity and inclination. The most precise pulsar timing is conducted on millisecond pulsars, which rotate hundreds of times per second with remarkable stability, serving as cosmic clocks that rival atomic clocks on Earth. Moving to higher energies in the electromagnetic spectrum, many neutron stars are potent sources of X-rays. Unlike radio emissions, which originate primarily from the magnetosphere surrounding the neutron star, X-rays often come directly from the neutron star's surface or from hotspots at its magnetic poles. These X-rays provide information about the temperature of the neutron star, which in turn offers insights into its age and internal composition. Because neutron stars gradually cool over time, their X-ray brightness serves as a cosmic chronometer. X-ray astronomy requires space-based observatories because Earth's atmosphere blocks X-ray radiation, protecting life on our planet, but hindering astronomical observations. Satellites such as NASA's Chandra X-ray Observatory, the European Space Agency's XMM Newton, and the more recent Nuclear Spectroscopic Telescope Array, or NuSTAR, have revolutionized our understanding of neutron stars by providing detailed X-ray images and spectra. These observatories have revealed the hotspots at the magnetic poles of pulsars, mapped the extended emission from pulsar wind nebulae, and discovered new populations of neutron stars that are not prominent radio emitters. Particularly fascinating are X-ray binary systems, where a neutron star is paired with a normal star. In these systems, matter from the companion star is drawn toward the neutron star by its powerful gravity, forming an accretion disk of superheated material. As this material spirals inward and eventually falls onto the neutron star's surface, it releases tremendous amounts of energy, primarily in the form of X-rays. By studying the patterns and spectra of this X-ray emission, astronomers can infer the neutron star's mass, rotation rate, and magnetic field strength, as well as investigate the behavior of matter under extreme conditions. Some neutron stars are also visible in optical light, though they are incredibly faint due to their small size. The first optical identification of a neutron star came in 1977 with the observation of the Crab pulsar, which appears as a faint 24th magnitude star at the heart of the Crab Nebula. This pulsar is visible not because we can see the neutron star's surface directly, but because we detect the optical component of the radiation produced by charged particles accelerated in its magnetosphere. Subsequent observations have identified optical counterparts for several other pulsars. Observing neutron stars in optical light requires large telescopes and sensitive detectors. Facilities such as the Hubble Space Telescope, the European Southern Observatory's Very Large Telescope, and the Keck Observatory in Hawaii have all contributed significantly to our understanding of neutron stars through optical observations. These observations complement radio and X-ray data, providing a more complete picture of the neutron star's properties and environment. Infrared observations offer another window into the world of neutron stars. While less common than radio or X-ray studies, infrared astronomy has revealed important aspects of neutron star behavior, particularly for magnetars. The strong magnetic fields of magnetars heat their surfaces, causing them to glow in infrared light. By studying this thermal emission, astronomers can estimate the temperature of the magnetar's surface and investigate how energy is transported in the presence of ultra-strong magnetic fields. At the highest energy end of the electromagnetic spectrum, gamma-ray astronomy has made significant contributions to neutron star research. The Fermi Gamma-Ray Space Telescope, launched in 2008, has detected gamma-ray emission from more than 200 pulsars, many of which were previously unknown. These gamma rays are produced by charged particles accelerated to near the speed of light in the neutron star's magnetosphere, providing insights into the extreme physics occurring in these regions. Gamma-ray telescopes have also played a crucial role in detecting magnetar outbursts. The most energetic flares from magnetars produce brief but intense bursts of gamma rays that can be detected across the galaxy. Instruments such as the Burst Alert Telescope on NASA's Swift Observatory and the Gamma Ray Burst Monitor on the Fermi satellite continuously monitor the sky for such events, allowing astronomers to catch magnetars in the act of flaring and quickly direct other telescopes to study the aftermath. Neutrino astronomy, though still in its infancy, has also contributed to our understanding of neutron stars. Neutrinos are nearly massless particles that interact very weakly with matter, making them difficult to detect, but also allowing them to escape directly from the interiors of dense objects like neutron stars. During the formation of a neutron star in a supernova explosion, vast numbers of neutrinos are produced as protons, and electrons combine to form neutrons. The detection of neutrinos from supernova 1987A provided direct confirmation of this process and offered valuable insights into the birth of a neutron star. Perhaps the most exciting recent development in neutron star observation has been the advent of gravitational wave astronomy. Gravitational waves are ripples in the fabric of space-time predicted by Einstein's general theory of relativity. Unlike electromagnetic waves, which interact with matter and can be absorbed or scattered, gravitational waves pass virtually unimpeded through any material, carrying pristine information about their sources. The first direct detection of gravitational waves in 2015, from the merger of two black holes, was a watershed moment in astronomy. This was followed in 2017 by the detection of gravitational waves from a binary neutron star merger, an event designated GW170817. The gravitational wave signal from this merger provided unprecedented information about the physical properties of neutron stars, including constraints on their size and rigidity, which in turn inform our understanding of the behavior of matter at extreme densities. What made GW170817 particularly groundbreaking was the coordinated observation of the event across the electromagnetic spectrum. Following the gravitational wave detection, astronomers observed a short gamma-ray burst, followed by an optical and infrared afterglow known as a kilonova, and later radio and X-ray emission. This multi-messenger observation of a neutron star merger represented a new era in astronomy, where cosmic events are studied through multiple and complementary information channels. The observation of neutron stars is not limited to detecting their radiation. In some cases, astronomers can study neutron stars by their influence on surrounding matter and light. For instance, the intense gravity of a neutron star can bend light rays passing near it, a phenomenon known as gravitational lensing. While direct imaging of such lensing around neutron stars is beyond current capabilities due to their small size, the effect has been observed in the timing of pulses from pulsars in binary systems, where the pulses are delayed when they pass near the companion star. Neutron stars in binary systems can also be studied through their effects on their companion stars. The intense gravity and radiation from a neutron star can cause its companion to be distorted, heated, or even gradually evaporated. By observing changes in the companion's light, astronomers can infer properties of the neutron star that would be difficult to measure directly. This technique has been particularly valuable for studying black widow and redback pulsars, systems where a millisecond pulsar is slowly destroying its low-mass companion. The future of neutron star observation looks exceptionally promising, with several major facilities under development or recently completed that will significantly enhance our capabilities. The Square Kilometre Array, a massive international project to build the world's largest radio telescope across Australia and South Africa, will dramatically increase our sensitivity to radio pulsars. It is expected to discover tens of thousands of new pulsars, potentially including exotic systems such as pulsar black hole binaries that would provide unprecedented tests of general relativity. In X-ray astronomy, missions such as the XRISM, or X-ray Imaging and Spectroscopy mission, a collaboration between Japan and NASA, will provide high-resolution X-ray spectra of neutron stars, revealing details about their composition and the extreme physics of their surfaces. The European Space Agency's Athena X-ray Observatory, planned for launch in the 2030s, will combine high sensitivity with excellent spectral resolution, enabling detailed studies of faint or distant neutron stars. For gravitational wave astronomy, upgrades to existing detectors like LIGO and Virgo, along with new facilities like KAGRA in Japan and LIGO India, will increase the detection rate of neutron star mergers from roughly 1 per year to potentially dozens annually. This will build a statistical sample of neutron star properties and provide more opportunities for multi-messenger observations. Looking further ahead, the Space-Based Laser Interferometer Space Antenna, or LISA, will be sensitive to gravitational waves from neutron star binaries long before they merge, complementing ground-based detectors that observe the final moments of these systems. Neutrino observatories such as IceCube at the South Pole and the planned Hyper Kamiokande in Japan will increase our ability to detect neutrinos from neutron star formation in supernova, potentially even allowing us to watch the birth of a neutron star in our galaxy in unprecedented detail. These observations would provide direct information about the conditions at the center of a collapsing star as it transforms into a neutron star. Technological advances are also enhancing our ability to extract information from observational data. Machine learning algorithms are being employed to detect faint pulsar signals in radio data that might be missed by traditional analysis methods. Improved computing power allows for more sophisticated modeling of neutron star interiors, atmospheres, and magnetospheres, facilitating more direct comparisons between theory and observation. And new statistical techniques enable astronomers to combine data from different observatories and wavelengths to extract maximum information about neutron star properties. One of the most tantalizing prospects for future neutron star observations is the possibility of directly imaging the surface of a neutron star. While this remains beyond current capabilities, the development of very long baseline interferometry in the radio and infrared, which effectively creates a telescope the size of Earth by combining data from widely separated observatories, is steadily improving our angular resolution. If these techniques can be extended to X-rays, where neutron stars are brighter, it might eventually become possible to resolve surface features on the nearest neutron stars, providing direct information about their size and surface conditions. Another exciting frontier is the search for continuous gravitational waves from isolated rotating neutron stars. If a neutron star has even a small asymmetry, a mountain or bump on its otherwise nearly perfect spherical surface, it will emit gravitational waves as it rotates. These waves would be much weaker than those from merging systems but persistent, allowing for long integration times to build up a detectable signal. Detection of such waves would provide information about the rigidity of neutron star crusts and the extent to which they can support deformations against their enormous gravity. As our observational capabilities continue to advance, we can anticipate many more discoveries about these fascinating objects. Neutron stars, once purely theoretical entities, have become increasingly well characterized through decades of innovative astronomical observations. Each new observational technique and instrument has revealed new facets of their behavior and properties, often in ways that were not anticipated. This ongoing process of discovery underscores a fundamental aspect of astronomy and science in general. Our understanding of the cosmos is intimately tied to the tools we use to observe it. As our observational windows on the universe expand through new wavelengths, messengers, and techniques, our comprehension of even the most extreme objects, like neutron stars, grows correspondingly richer and more complete. The history of neutron star astronomy is a testament to human curiosity and ingenuity, a story of persistent efforts to understand these cosmic extremes, despite the observational challenges they present. As we continue to observe these extraordinary stellar remnants across the electromagnetic spectrum and beyond, we not only learn about neutron stars themselves, but also about the fundamental laws of physics under conditions impossible to recreate on Earth. In their light, their gravitational waves, and their influence on their surroundings, neutron stars reveal the workings of nature at its most extreme, connecting the microscopic world of subatomic particles with the macroscopic realm of astrophysical phenomena, and reminding us of the profound unity underlying the diverse phenomena of our universe. Despite decades of intensive study and remarkable progress in understanding neutron stars, these extraordinary objects continue to challenge scientists with numerous unresolved questions. The extreme conditions within neutron stars, far beyond what can be replicated in terrestrial laboratories, create a natural frontier where our current theories of physics are pushed to their limits and possibly beyond. In this realm of the superdense and supermagnetic, many fundamental questions remain open, driving theoretical speculation, observational campaigns, and experimental efforts aimed at unraveling the mysteries of these cosmic laboratories. Perhaps the most fundamental open question concerns the equation of state of matter at supranuclear densities. The equation of state describes the relationship between pressure and density in the interior of a neutron star, essentially telling us how matter behaves when squeezed beyond nuclear densities. This question lies at the intersection of nuclear physics, particle physics, and astrophysics, connecting the microscopic world of subatomic particles with the macroscopic realm of stellar remnants. Current uncertainties in the equation of state lead to significant variations in predictions about neutron star properties. Depending on which theoretical model is adopted, the maximum mass for a neutron star could range from about 2 to 3 solar masses, and the typical radius for a 1.4 solar mass neutron star could be anywhere from about 10 to 14 kilometers. These uncertainties reflect our incomplete understanding of how matter behaves under extreme compression. Several approaches are being pursued to constrain the equation of state. Observations of the most massive known neutron stars, currently around 2.1 solar masses, eliminate equations of state that predict lower maximum masses. Similarly, measurements of neutron star radii through X-ray observations can rule out equations of state that predict radii outside the observed range. Most promising are gravitational wave observations of neutron star mergers, which provide information about how neutron stars deform under strong gravitational fields, directly probing their internal structure. Laboratory experiments also contribute to this effort. Heavy ion colliders, such as the relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN, create tiny fireballs of extremely hot and dense matter by smashing atomic nuclei together at nearly the speed of light. While these experiments cannot reach the densities found in neutron star cores, they provide valuable data about nuclear matter under extreme conditions, helping to constrain theoretical models that are then extrapolated to neutron star densities. Closely related to the equation of state question is the mystery of what exactly exists in the deepest interiors of neutron stars. While the outer layers are reasonably well understood to consist of a crystalline crust of neutron-rich nuclei transitioning to a fluid of primarily free neutrons with some protons and electrons, the core composition remains highly uncertain. Several possibilities have been proposed for the core. The conventional picture suggests a continuation of the neutron-dominated fluid, perhaps with an increasing fraction of protons, electrons, and muons at higher densities. However, more exotic possibilities include the appearance of hyperons, particles similar to neutrons and protons, but containing one or more strange quarks. These hyperons, such as the lambda and sigma particles, might become energetically favorable at the extreme pressures in neutron star cores, significantly altering the equation of state. Even more exotic is the possibility of a phase transition to deconfined quark matter in the innermost regions. Under normal conditions, quarks are confined within protons and neutrons, unable to exist freely due to the properties of the strong nuclear force. However, at sufficiently high densities, theory suggests that quarks might become deconfined, creating a state of matter where quarks move freely over macroscopic distances. If this occurs in neutron star cores, it would create what is effectively a giant subatomic particle spanning several kilometers. This possibility leads to the fascinating concept of hybrid stars, neutron stars with conventional neutron matter in their outer regions, but deconfined quark matter in their cores. More extreme are the hypothetical strange quark stars, objects composed almost entirely of deconfined up, down, and strange quarks. Some theories suggest that strange quark matter might be the true ground state of matter at high densities, meaning it would be energetically favorable compared to ordinary nuclear matter. If true, this would raise the possibility that some objects currently classified as neutron stars might actually be strange quark stars. The challenge in distinguishing between these possibilities lies in the difficulty of directly observing the cores of neutron stars. While various observational signatures have been proposed that might differentiate conventional neutron stars from those with exotic cores, such as differences in cooling rates or maximum masses, current data remains insufficient to make a definitive determination. This question remains one of the most exciting open frontiers in neutron star physics, with potential implications for our understanding of the fundamental nature of matter. Moving from the interior to the surface, significant questions remain about the physical conditions at the boundary between a neutron star and the surrounding space. The composition and structure of neutron star atmospheres, though incredibly thin by terrestrial standards, play a crucial role in shaping the observable properties of these objects. The exact composition likely varies depending on factors such as temperature and magnetic field strength, with possibilities ranging from hydrogen and helium to heavier elements like iron. In magnetars, the extremely strong magnetic fields are expected to create highly unusual surface conditions, where atoms are distorted into elongated, needle-like shapes and conventional chemical bonds are disrupted. Under such conditions, the surface may form a kind of crystalline structure unlike anything found on Earth. These exotic surface states could influence the thermal and radiative properties of magnetars, potentially explaining some of their unique observational features. Questions also persist about the boundary layer between the solid crust and fluid interior of neutron stars. This transition region may play a crucial role in various phenomena, including pulsar glitches, sudden increases in rotation rate thought to result from the transfer of angular momentum from the superfluid interior to the crust. The exact mechanism of this transfer and the nature of the crust-fluid coupling remain areas of active research, with implications for our understanding of superfluidity on astrophysical scales. The magnetic fields of neutron stars present another set of open questions. While the basic mechanism for generating the strong fields observed in young neutron stars is reasonably well understood as a consequence of flux conservation during the core collapse of the progenitor star, the origin of the ultra-strong fields in magnetars, often 1,000 times stronger than in typical neutron stars, remains debated. The leading theory involves a dynamo mechanism operating in the first few seconds after the neutron star's birth. But the details of this process and why it occurs in only a fraction of neutron stars are still uncertain. Equally puzzling is the long-term evolution of neutron star magnetic fields. Observations suggest that magnetic fields decay over time, but the rate and mechanism of this decay are not fully understood. Processes such as ambipolar diffusion, where the magnetic field drifts relative to charged particles, and Hall drift, where the field is carried by electron currents, likely play important roles, but quantitative predictions remain challenging. This magnetic field evolution is crucial for understanding the life cycles of different neutron star populations and their relationships to one another. The connection between neutron stars and their progenitor stars represents another area of uncertainty. While it is generally accepted that neutron stars form from the collapsed cores of massive stars, the exact mapping between progenitor properties such as mass, rotation, and magnetic field, and the resulting neutron star characteristics remains unclear. This connection is complicated by the complex physics of the supernova explosion itself, where asymmetries and instabilities can significantly influence the properties of the remnant. Recent three-dimensional simulations of core collapse supernovae have begun to shed light on this process, revealing the crucial role of neutrino heating and hydrodynamic instabilities in powering the explosion. These simulations suggest that the formation of a neutron star is not a simple, spherically symmetric process, but rather a chaotic and asymmetric one, potentially imparting significant kicks and spins to the newborn neutron star. However, these simulations remain computationally intensive and sensitive to input physics that is not fully constrained, leaving many questions about the supernova neutron star connection unanswered. The observed diversity of neutron star types, from radio pulsars to magnetars to central compact objects, raises questions about their evolutionary relationships. Are these distinct populations or different manifestations of the same objects at various stages of their lives? Evidence increasingly suggests interconnections between these categories, with some magnetars showing pulsar-like behavior and some pulsars exhibiting magnetar-like outbursts. A unified evolutionary picture is emerging, but many details remain to be worked out. Particularly intriguing is the role of neutron stars in producing cosmic phenomena such as fast radio bursts, millisecond duration flashes of radio emission of unknown origin. The discovery of a fast radio burst associated with a galactic magnetar in 2020 provided compelling evidence that at least some of these enigmatic events are produced by highly magnetized neutron stars. However, the precise mechanism for generating the bursts and whether all fast radio bursts share the same origin remain open questions, highlighting the continuing capacity of neutron stars to surprise astronomers with unexpected behavior. The process of neutron star cooling presents another set of unresolved questions. Neutron stars are born extremely hot, with temperatures exceeding 1 trillion degrees, but cool rapidly through neutrino emission and more slowly through photon emission from their surfaces. The observed temperatures of neutron stars of different ages provide crucial constraints on their internal composition and structure, as different cooling mechanisms operate depending on what particles and states of matter are present. Some neutron stars appear to cool faster than standard models predict, possibly indicating the presence of exotic particles or states in their interiors that facilitate enhanced neutrino emission. Others, particularly magnetars, seem to maintain higher temperatures than expected for their ages, suggesting additional heating mechanisms, possibly related to the decay of their strong magnetic fields. A comprehensive theory of neutron star thermal evolution that accounts for this diversity of behaviors remains to be developed. The phenomenon of pulsar nulling, where a pulsar temporarily stops emitting radio pulses before resuming, sometimes after hundreds or thousands of rotation periods, remains poorly understood. Similarly, the mode changing observed in some pulsars, where they switch between different patterns of radio emission, challenges our understanding of the emission mechanism. These phenomena suggest complex dynamics in the pulsar magnetosphere that current models do not fully capture. For millisecond pulsars, questions persist about the recycling process that spins them up to their rapid rotation rates. While the basic concept of spin-up through accretion from a companion star is well established, details such as the efficiency of angular momentum transfer, the evolution of the binary system during this phase, and the origin of the observed diversity in millisecond pulsar properties remain areas of active research. The recent observation of gravitational waves from neutron star mergers has opened new avenues for investigation, but also raised new questions. The fate of the merger remnant, whether it forms a black hole immediately or passes through a phase as a hypermassive neutron star, depends on the total mass and the equation of state, both areas of continuing uncertainty. The exact nucleosynthesis processes during the merger and in the ejected material, vital for understanding the cosmic origin of heavy elements, also remain to be fully characterized. Looking beyond conventional neutron stars, several hypothetical objects representing variations on the neutron star theme have been proposed. Quark stars, as mentioned earlier, would consist primarily of deconfined quark matter rather than neutrons. Electroweak stars might form as an intermediate state between neutron stars and black holes, supported against collapse by the pressure of electroweak quantum effects. Q stars, supported by a form of dark energy, and boson stars, composed of bosonic rather than fermionic matter, represent even more speculative possibilities. While no definitive evidence for any of these exotic alternatives has been found, they remain theoretically intriguing and potentially observationally distinct from conventional neutron stars. The continued search for such objects, or constraints on their existence, connects neutron star astronomy with fundamental questions about the nature of matter and the possible states it can assume under extreme conditions. Neutron stars also offer potential windows into physics beyond the standard model of particle physics. Their extreme conditions might allow for phenomena not observable in terrestrial experiments, such as the conversion of photons into hypothetical axions in strong magnetic fields, or the effects of quantum gravity near the surfaces of the most massive neutron stars. While speculative, such possibilities highlight the role of neutron stars as natural laboratories for fundamental physics. The search for planets around pulsars, following the surprising discovery of the first confirmed exoplanets around pulsar PSRB 1257+12 in 1992, represents another open area of investigation. These pulsar planets raise questions about their formation, whether as survivors of the supernova that created the pulsar, or as second-generation planets formed from the debris disk afterward. The extreme environment around a pulsar, with intense radiation and the history of a violent supernova, makes these planetary systems particularly puzzling and intriguing. Perhaps the most fundamental open question is whether our current theories of physics are adequate to fully understand neutron stars, or whether new physics beyond our current framework might be required. Neutron stars operate in regimes where quantum mechanics, nuclear physics, and general relativity all play crucial roles, yet a fully unified theory incorporating all these aspects remains elusive. The continuing study of neutron stars might provide vital clues or constraints for theoretical efforts to develop such unified descriptions of nature. As we reflect on these open questions, it becomes clear that neutron stars, despite being studied for over half a century, remain at the frontier of astrophysics and fundamental physics. Each answered question seems to raise new ones, and each new observation or theoretical advance adds layers of complexity to our understanding. Yet this ongoing process of discovery and refinement is the essence of science, a testament to both the complexity of the universe and the human capacity to progressively unravel its mysteries. The quest to understand neutron stars connects some of the largest objects in the universe with some of the smallest, linking the cosmic with the quantum in ways that challenge and extend our comprehension of nature. In their extreme densities, strong gravity, and powerful magnetic fields, neutron stars continue to serve as cosmic laboratories, pushing the boundaries of known physics and potentially pointing the way toward new theoretical frameworks. As we gaze at the night sky, contemplating the diverse phenomena that neutron stars manifest, from the regular pulses of radio pulsars to the dramatic flares of magnetars. We are witnessing the consequences of physics operating at extremes far beyond our everyday experience. In their mysteries and open questions, neutron stars remind us of how much remains to be discovered about the universe and its fundamental workings, inviting continued exploration and inspiring wonder at the extraordinary phenomena that nature produces when ordinary matter is pushed to truly extraordinary conditions. As our journey through the realm of neutron stars draws to a close, we find ourselves contemplating objects that exist at the very edge of comprehension, where matter is crushed beyond what our intuition can grasp, and the familiar rules of physics are stretched to their limits. These stellar remnants, these cosmic pebbles bearing the mass of suns, stand as monuments to the extraordinary diversity of our universe and the remarkable journey that matter undertakes throughout cosmic history. Consider for a moment the extraordinary density that defines a neutron star. In our everyday world, density is a simple concept, the measure of how much mass is contained within a given volume. A piece of lead feels heavy for its size because it is dense, with atoms packed closely together. Yet the densities we encounter in daily life pale in comparison to what exists within these stellar remnants. The human body has a density similar to water, about 1 gram per cubic centimeter. The core of our planet, composed primarily of iron and nickel under immense pressure, reaches a density of roughly 13 grams per cubic centimeter. The core of the Sun, where nuclear fusion transforms hydrogen into helium, has a density of about 150 grams per cubic centimeter. Yet the average density of a neutron star exceeds 10 to the 14th grams per cubic centimeter, more than 100 trillion times denser than water. If Earth were compressed to the density of a neutron star, our entire planet would fit within a sphere less than 500 meters in diameter, roughly the size of a small mountain. The mass of all human beings on Earth, compressed to neutron star density, would fit within a volume smaller than a raindrop. Such comparisons strain our capacity to visualize, highlighting how far these objects lie beyond our everyday experience. This extraordinary density arises from the removal of the empty space that ordinarily exists within and between atoms. In conventional matter, the actual particles, the nuclei and electrons, occupy only a minuscule fraction of the total volume, with vast empty spaces between them, similar to how our solar system consists mostly of empty space between the planets. In a neutron star, this emptiness has been squeezed away, leaving a densely packed sea of neutrons in direct contact with one another, their quantum mechanical properties now the primary force resisting further collapse. Yet a neutron star is not merely a cosmic curiosity, a quirk of nature's extremes. It is a crucial participant in the grand cosmic story, a vital link in the chain that connects the primordial hydrogen, formed in the Big Bang, to the diverse elements that compose our bodies and our world. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in the nuclear furnaces of stars that lived and died before our sun was born. And the heaviest elements, the gold and platinum and uranium, owe their existence in part to neutron stars, either through the violent mergers we have explored, or through the rapid neutron capture processes in supernova explosions that give birth to these stellar remnants. In this sense, our connection to neutron stars is intimate and profound. We are, in a very real way, the children of stars, our bodies composed of atoms that have journeyed through the cosmos for billions of years, some perhaps having been part of a neutron star merger that scattered gold and other heavy elements across interstellar space. The wedding ring on your finger, the platinum in a catalytic converter, the uranium that powers nuclear reactors, all bear the imprint of processes involving neutron stars, cosmic alchemists that transform the elements through conditions impossible to replicate on Earth. Beyond their role in cosmic chemistry, neutron stars serve as natural laboratories for physics under extreme conditions. The densities, pressures, magnetic fields, and gravitational fields found in and around neutron stars far exceed anything we can create in terrestrial experiments. By studying these objects, scientists can test theories of nuclear and particle physics, general relativity, and quantum mechanics in regimes otherwise inaccessible, potentially revealing new insights into the fundamental nature of matter, energy, space, and time. The recent advent of gravitational wave astronomy, with the direct detection of ripples in space-time from neutron star mergers, has opened an entirely new window onto these extraordinary objects. For the first time, scientists can directly sense the distortions of space-time caused by accelerating masses, providing information complementary to that obtained through the various forms of electromagnetic radiation. This multi-messenger approach, combining gravitational waves with observations across the electromagnetic spectrum, promises to revolutionize our understanding of neutron stars and their role in the universe. As we gaze up at the night sky, the stars we see with our naked eyes are primarily main sequence stars like our Sun, steadily converting hydrogen to helium through nuclear fusion, or giant stars in the later stages of their evolution. Neutron stars, despite their exotic nature, are typically too small and too faint to be visible without powerful telescopes. Yet among the points of light scattered across the darkness, there exist these stellar remnants, these cosmic lighthouses, silently spinning and occasionally flaring, marking time with their rhythmic pulses and bearing witness to some of the most extreme conditions in the universe. Consider the Crab pulsar, the neutron star at the heart of the Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 CE. This neutron star, spinning 30 times per second and sweeping its beams of radiation across our line of sight with clock-like precision, has been keeping this rhythm for nearly 1,000 years. It will continue to do so long after our brief lives have ended, gradually slowing its rotation as it loses energy, a cosmic timekeeper marking the passage of centuries with each of its trillion pulses. Or consider the binary neutron star systems scattered throughout our galaxy, gradually spiraling closer to one another as they emit gravitational waves, each orbit bringing them incrementally nearer to their eventual merger. Some of these systems may have formed billions of years ago from pairs of massive stars that lived and died together. Their orbital decay is imperceptibly slow from a human perspective, yet inevitable on cosmic timescales. A dance of death that will culminate in a burst of gravitational waves and electromagnetic radiation that may someday be observed by our descendants, should humanity endure. The magnetars, with their colossal magnetic fields, occasionally announce their presence with giant flares, releasing in a fraction of a second as much energy as our Sun emits in hundreds of thousands of years. These flares, crossing vast interstellar distances, remind us of the enormous energies contained within these small but mighty stellar remnants, energies that dwarf anything in our everyday experience and connect to the fundamental forces that shape our universe. As we conclude our exploration of neutron stars, we are left with a sense of wonder at the diversity and complexity of the cosmos. From the quantum mechanical behavior of subatomic particles to the macroscopic effects of extreme gravity, from the nuclear processes that forge elements to the gravitational waves that ripple across space-time, neutron stars encompass and connect diverse aspects of physical reality. They remind us that the universe is not just stranger than we imagine, but stranger than we can imagine, filled with objects and phenomena that challenge our intuition and expand our understanding. Yet within this strangeness, there exists a profound order, a set of physical laws and principles that, while sometimes counterintuitive, consistently govern the behavior of matter and energy throughout the cosmos. Neutron stars, despite their extreme nature, follow these same laws that govern our everyday world. They simply push these laws to their limits, revealing aspects of physics that remain hidden under ordinary conditions. As you drift towards sleep beneath the canopy of stars, consider the neutron stars among them. These cosmic beacons pulsing in the darkness, their beams sweeping through space like cosmic lighthouses. Though invisible to the naked eye, they are there, representing nature's experiments in extreme physics, silently teaching us about the limits of matter and the vastness of cosmic possibilities. In their steady pulses and occasional flares, in their spiraling dances and catastrophic mergers, neutron stars embody the dynamic and ever-changing nature of the cosmos. They remind us that even in death, stars continue to influence their surroundings and contribute to the grand cosmic story. From their birth in the fiery furnace of a supernova to their eventual fate, whether cooling into invisibility or merging to form black holes, neutron stars participate actively in the ongoing evolution of the universe. And so, as consciousness fades and sleep approaches, carry with you the image of these extraordinary objects, these cosmic extremes where matter is compressed beyond ordinary comprehension and magnetic fields reach strengths that bend the very vacuum of space. Let the rhythmic pulses of distant pulsars guide you into dreams, perhaps dreams of a universe even stranger and more wonderful than the one we have explored together. A universe where the boundaries of the possible are continually expanded by discoveries yet to come. For in the end, the story of neutron stars is also our story, a chapter in the grand narrative of matter and energy throughout cosmic history. From the Big Bang to the formation of galaxies, from the birth and death of stars to the emergence of planets and life, we are connected to these distant objects through the shared heritage of atoms and the universal laws of physics. In their extreme densities that defy imagination, neutron stars remind us of how far matter can be transformed while still following the same fundamental principles that govern our own existence. Rest now under the silent watch of these cosmic sentinels, these stellar remnants that have witnessed the passage of eons and will continue their cosmic dance long after we are gone. In their ancient light and gravitational whispers, we glimpse not just the extremes of the present universe, but echoes of its past and hints of its future. A cosmos of infinite wonder awaiting continued exploration by curious minds seeking to understand nature at its most fundamental and most extreme.